Okay, so that's a pleasure, a great pleasure to have Juliana Bueno-Soler and Walter Carnielli with us. I think that most of you, if not all of you, already met them because they have some 2 months more than. But I would like to tell you the story of their being here because it's quite a nice story. I know Bruno and Juliana from many times.
Change my name?
Yes,
Bruno?
because of Bruno. Walter, and I don't know why Bruno, I don't know. Walter and Juliana a lot of time because I invited them in Paris, they invited me in Campinas, we met in different conferences, so we are calling from long time. And so it happened that I met them in the International Congress of Logic, Methodology and Philosophy of Science in Buenos Aires in summer 23, and so you find a colleague that you like. Ah, Walter,
Ciao,
ciao. Hi, Juliana, how are you? How are you? Fine, fantastic. What do you go to eat to have lunch today? You go there, so okay, perhaps this night. And then Walter said to me, you know, I would like a suggestion by you, for perhaps you can help me because I have some fund by a Brazilian project to spend 6 months in the United States, but I do not know real where to go. So don't you have some good suggestion? And they said, of course that I want. Chapman. And I said, Chapman? This Chapman. Chapman is a very nice university, so on, so on. So it was perplexed in the beginning. But then I explained it to him and to Juliana all the benefit to be in Chapman. So he decided to accept. He was a little bit skeptic, but I think that now he's very happy. You know, to be so happy that he just asked me, "How can I come back?"
Yeah. Sure.
And so now this is Walter Carnielli and Juliana Bueno-Soler, How to Benefit from Uncertainty, an Introduction to Paraconsistent Bayesian Update. Why an example of uncertainty? Will then be able to come back? I hope yes, but still it's not completely sure.
I hope so. Thank you very much. So it's indeed my pleasure to be here. I'd like to thank Marco, Drew as well, Jose, and other people that wrote letters for us. I mean, accepting our stay here. We are really very happy to be here. We think it's a very nice university with lots of nice ideas, including this engineering of different seminars like students make on previous days. A very nice idea. We're sort of copying that idea in Brazil as well, because it's wonderful. People can, I mean, really learn how to make questions, how to discuss, how to be, without being ashamed of being questions or discussing or talking to professors or to colleagues. So really nice. The university is really wonderful, very well organized. Tell you frankly, I know many in the whole world, including Paris, Berkeley, São Paulo, Campinas, Luxembourg, Germany, many places, etc. Portugal. This is one of the most nice, I mean, agreeable one. So I'm very happy to hear. Today I'm going to tell you, so it was a paper that I prepared with Juliana on Paraconsistent Bayesian update. What is this story? I mean, yesterday Juliana gave some previous hints, but I do everything again with more, let's say, more technical details. First of all, let me start talking about what is paraconsistent about. Paraconsistency is a philosophical position about logical consequence, rejecting the law of ex contradictione quod libet, from contradictions you take anything else, or law of explosion. It's just, but then the things are not so easy. It's not a matter of deleting a logical law. When you delete a logical law, it's like you are running with a horse with 3 legs, right? You have to find a way to make the horse work and carry you. So I have to repair everything. We have to do a kind of an engineering. It's a new proof theory, a new semantics, a new everything. So it's because you are weakening the logic, the power of logic, then you have to rework everything again. And why do we weaken logic? Because classical logic is too stupid. Actually, I have to say. Why is it so stupid? Because it was designed to do mathematics. And nowadays we use logic not only for the foundations of mathematics, we use the logic for the foundations of probability, for computer science, for engineering, for many others.
Are you saying that mathematics are stupid? Are you saying that mathematics are stupid or mathematicians?
No. The classical logic is stupid. Mathematicians are very nice. I'm a mathematician myself. I have a PhD in mathematics and algebra. So, what can I say? That kind of thing about mathematics. I love it. But classical logic is too stupid. Even mathematicians don't need it. They accept it. They bought the package. They don't need it. They don't even need these famous laws of explosion. It's not necessary. So let's get rid of it. By getting rid of it, you have to rework everything again. Okay. So then, paraconsistent is a philosophical position where you get rid of this law and you have to reconstruct everything again. Why?
But I'm very sympathetic what you say, but you go a little bit too quick according to me.
Am I?
Because you say that explosion is not needed. In a sense, I understand that explosion is not needed because I saw no mathematician never that prove a P because it's the result of a contradiction. So of course, from a contradiction follow a lot of theorems, but normally a theorem is not proved as a consequence of a contradiction. So of course, in this sense, it's not needed. But on the other sense, in a sense, it's needed because a proof by absurd that finish with a contradiction is exactly something that we use. So if we reject explosion, we still should be able either to renounce to prove a contradiction or to give another reason to accept the proof by contradiction.
You can maintain the law proofs by contradiction.
Okay, so this is the point.
You can maintain. I'm not rejecting anything. Because, this law of explosion is not, it has no operative content on it. It's just a stop sign. Just a stop sign. Don't go there. Here be dragons. And they go a little bit further, you see no dragons. See? So, okay. Then paraconsistency comes in two branches. I think I have to explain that. Adjunctive, which is called stronger paraconsistent logic, and non-adjunctive logic. A non-adjunctive system is a system that does not validate conjunction. So, from A, B, you do not derive the conjunction of A and B.
Very nice.
So some logics are like that. So non-adjunctivism means that an agent can maintain contradictory beliefs, like I believe in A, and I believe in negation of A, while not believing in contradictions as A and not yet.
One question. I understand the point, but why you generalize adjunction? I like the fact that adjunction is not generalized. I like very much that A and B do not follow A and B, because I have a lot of examples in which this does not happen. But it seems to me that now you are doing that, not for this other example, but simply to avoid contradiction. So why you don't say from A and non-A does not follow A and non-A? So why you take B to be whatever B, rather than non-A in particular? So why is the generality?
Well,
you could not simply stay to a particular case of that.
I see. You could sort of be half adjunctivist, right? I don't do for that kind of thing. I don't for the. You could be. That position does not exist. That you can invent.
That position does not
exist yet, but you can invent one. Marco Panza's position on adjunctive.
No, I know, because I like very much. That is not adjunctive system. I like very much that the conjunction introduction seems to me that is a crazy law.
Yes, but I give you an argument because why we don't take that position. We prefer to be really, frankly, adjunctivists. I explain why.
Okay.
Why? So this is non-adjunctivism. Then you have adjunctivism. That for someone that believes A and B, he's committed to believe the conjunction of A and B. Okay. Why do we adopt this adjunctive view? Because in this way, we could assign a non-zero probability to contradictions. I'm very much interested in attributing probabilities to crazy things like A and not A, which classically in standard probability have zero measure. And here I want to give a measure to it. I think it's going to be clear in a moment why. So, for example, in an election poll with 1,000 people, for instance.
Are you sure that is a good example to do today?
After that, afterwards. This is going to explain why people make mistakes. Huh? It's 1,000 people, so suppose that 6% of the respondents prefer candidate A to B, while another channel, television or wherever, or Nate Silver, says that 70% of the other people prefer B to A, so there is 30% of confusion, contradiction, inconsistency in the middle of it. Okay? So this is a very big, this is the enormous problem, like too much to be accepted. But on the other hand, if only 5% or 3% or 1% of the respondents are conflicting, then you can accept it better. So my point is here the following. Not all contradictions have the same. Not all contradictions are equally dangerous. Some of them are less dangerous than others, depending on how they weight. Okay? And by accepting this adjunctive position, we can make that difference. We can measure that difference. Okay? So, there are many different kinds of paraconsistent logic, many ones by Graham Priest in Australia, by Battens in Belgium. There is people in New Zealand, Israel working. There is very wide kind of research going on everywhere. We are going to use the so-called Brazilian, like the samba contradiction, samba paraconsistent logic, which is.
But the Brazilian paraconsistent logic began with Newton?
Yeah. Well, with Newton, that's a very controversial. With Newton on one hand, and with Jaskowski, Stanisław Jaskowski in Poland on the other hand. Jaskowski was more concerned with a semantical side, explaining contradiction by his dialogical or discursive, yes, exactly. Discursive, nobody knows exactly what it was. Explaining how semantically contradictions could arise, and Da Costa was more busy making a system with axioms and kind of thing, more independently, right? So, they had two fathers. Okay, so these LFIs are the logics of formal inconsistency. It was a very wide way of building paraconsistent logic, is in the sense that most of the other logics that the people construct fall into this model, this kind of engineering model for building logic. So the basic tenets of the LFIs are the following. Contradictions and inconsistency are not the same. Okay, I'll give more example in a moment. And to be contradiction-free is not the same as to be consistent. This is very important because, the fathers of logic or fathers of law like Hilbert, Gödel, and Frege, for all those people, Umberto Russell, etc., for them to be consistent is to be exactly free of contradictions. And in our case, it's not like that. It's not like that. So we're not conflating those two notions. They are different for us. They can be conflated. They can be conflated and returning to the initial position, if you wish, if you put some axioms. So in principle, they are different. Our point here is that we need to pay some extra cost for axioms to make them return to the point where consistent is exactly the same as freedom from contradiction, as Gödel was working with, for instance, with his program of Hilbert, etc. So they are then not explosive in the sense that A and not A does not entail all possible B, for arbitrary B, but on the other hand, they are controllably or gently explosive in the sense that A contradiction plus, no, sorry, it's wrong here. It should be, that's my mistake. It's both A and not A entails B for arbitrary B, not entails, sorry. You know?
So if A
Is there a
is
pointer?
consistent, so if A is consistent, then it does explode.
I'm looking for a pointer, don't have a pointer. Anyway, it's better written than
There's a
later.
stick in the corner, I don't know whether that helps.
What you need?
Pointer? No, that's okay.
It wouldn't work
I
because.
pointer, yes, yeah. Yes, I got it.
Oh, you mean like.
Anyway, it's my mistake.
dangerous.
What I mean is,
This won't
if
show for the-
something is,
So you have two choices.
okay,
You want only to indicate this one. If you want to beat the people that contradict this one.
I learned to be, okay. If I don't destroy the monitor. Okay, that's my mistake here. I'm very sorry. That means consistent A and contradictory A really explodes. Sorry, really explodes. So, in other words, contradictions do not lead to explosion unless they are consistent. Now you're going to ask me what's to be consistent. Let me try to explain to you what's to be consistent. Think about the Goldbach conjecture. I'm trying to give an example. I took lots of time to think about an example. Let me see if it works, right? Think about the Goldbach conjecture. The Goldbach conjecture is the following statement. Every even natural number greater than 2 is the sum of two primes. Wonderful, beautiful conjecture, open conjecture. Nobody knows how to prove it. Nobody ever found a counterexample. All even number we can think can be written as a sum of two primes, for billions and billions of examples, but no proof. Okay. Now, contradiction requires a negation. Like I can say, G, sentence G, statement G. Goldbach conjecture has a counterexample, and not G. Goldbach conjecture has no counterexample. Suppose you were discussing, Alex and me, and he says, okay, has a counterexample, and say, no, there's no counterexample. No, this is not acceptable. Why is not acceptable? Because having a counterexample, right? Having a counterexample is something objective, verifiable. If he says, I have a counterexample, I ask him, please show me. If I say, there's no counterexample, I say, okay, prove it. Completely objective. So this is consistent statement. Some statements are consistent. They cannot stand any contradiction. So here, G and not G is supposed to be consistent because why is it supposed to be consistent? Because we agree that mathematical statements are the queen of consistency.
Even if we cannot prove that they are.
Even if you cannot prove, but who does not believe it? If someone does not believe that mathematics, arithmetic is inconsistent, better don't go to college, right?
There were a moment in which Nelson was trying to prove that there is a contradiction in time arithmetic.
Yeah. Okay, but you know, this is consistent. Consistent is something that we agree that is completely hard thing that cannot stand any contradiction. Now, on the other hand, inconsistent is something different. It's not to be contradictory. I mean, inconsistent means I found lots of synonymous for dissonant, disharmonious, incongruous, disjointed, discordant, incongruous, incoherent, mismatched, conflicting, disconnected. Is any other?
Walter,
Lacking harmony.
I have another synonymous.
Which one?
Walter.
Me? I'm not synonymous, I'm a noun. So it's something that's not working. Like, for instance, in a musical performance, one player can be out of tune or off beat, creating discordant sounds. There's no contradiction in sounds. There's just a disharmony or unharmony or whatever. Right? Now, suppose taking the same Goldbach conjecture example again, take another statement, G prime says the following. Goldbach conjecture is acceptably true. It is, because nobody could find any counterexample in billions and billions of attempts. So it is acceptably true. Another person says, well, I myself say the same thing. Well, on the other hand, it is not acceptably true, because there's no proof yet. You is living, and he told me, not because he does not agree, because
But now I disagree, so.
Okay. Thank you.
Sorry.
Thank you. If I say that acceptably true and not acceptably true, this word acceptably makes it more softy. Now, it does not generate any trivialization because it's by itself inconsistent. It's not hard. Inconsistent is only softy, disharmonious, blah, 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 right? I hope I can convince you about that difference. I only ask you to buy that small distinction between consistent or inconsistency and contradiction. If you buy that there is a difference, then we are done. I can do logic as beautiful as you like with model theory, proof theory, the same computer problem is about feasibility happens here, NP completeness, blah, 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 blah. All the classical discourse applies here again, if you accept that small distinction. Right? So I can think that statements are by default not consistent or even inconsistent. I mean, I use this black ball to mean inconsistency. You can ask me the following: is inconsistent the negation of consistent? It could be. In this system, in my system, don't the system here, they are taken to be primitive, both of them. But you can just add one little axiom that says black ball is the negation of white ball, right? Like that. And just make clear that I'm not making modal logic here. So black ball is just a negation. I could add that. I don't have it. In this system here, I have inconsistent and consistent taken as primitive. And please, it's not that I'm doing not consistent not. No. It's not like the same distinction between modalities, like in necessity and possibility. Okay, good. Now, this idea makes us to take the following position: contradictions are not all the same. That's concerned with the spirit of this LFI, is the logical form of inconsistent, right? A contradictory theory is not necessarily trivial, provided the contradiction does not refer to something inconsistent. Have you seen that already? This flexibility of the LFIs is due to the principle of horizontal explosion, which is a kind of a tamed principle of explosion. So this principle says that now it's correctly written, consistently alpha and not alpha entails every possible beta, although alpha and not alpha does not entail all possible beta, or it fails to entail beta for some reason, right? So in the LFIs, not all contradictions are equivalent, and not all contradictions may cause deductive triviality. They expand the classical logic. I mean, we are not making any revolution here, like intuitionistic logic, that you are rejecting some basic principle. We're not rejecting anything. Just expanding the limits of logic so that classical stance, the classical logic can be recovered by simply supposing that all kinds of propositions are consistent. So a classical logician is a special paraconsistent logician who accepts white ball in front of all his or her statements. That's all. Okay?
So a classical logician is a stupid paraconsistent logician.
Yes. I wouldn't say that, because lots of our friends are classical logicians, but
That's what you
except that
say.
logic
It's not what I say myself.
No
It is what
logician.
you say.
Okay, if you like, if you're brave enough. Okay, the backbone of this logic is, I'm presented here, is the logic named LETF, Logic of Evidence and Truth. It was designed to formalize the notion of evidence, which is a sort of a forgotten notion. People speak about doxastic logic, epistemic logic, blah, 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 blah. So they like epistemic operators, possibility, knowledge, belief, blah, 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 many of them. But the notion of evidence is a bit forgotten mathematically in a certain sense. Right? So this logic here was built, was designed to incorporate the notion of evidence. Okay. So mathematically, it can be designed in several different ways, but here I have my connectives, primitive connectives like a white ball, consistent, black ball, inconsistent, conjunction, disjunction, and negation. I don't have any implication here.
Why you need the two ball as primitive? You can one.
I can add this axiom here if I like, and make them definable one from the other. But here we prefer not to use more axioms than necessary. You don't need it. Okay, so this is completely classical. What I'm doing here, I'm putting these natural deduction rules, which are all of them classical rules. So what's the difference from classical logic? The difference is that those rules are not sufficient to characterize classical standard logic. They are all fine. All of them are valid in classical logic, like De Morgan rules, introduction of connectives, elimination of connectives, blah, 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 blah. All the classical ones, double negation, reduction, etc. What is missing is this yellow guy here. This logic has only two missing items. That's the law of explosion and law of excluded middle. Principle of excluded middle. Okay, those two are taken out of the logic, and then it has less power. It's more dangerous. It's not like an explosive by itself. Not so stupid, as I say. They're more gentle, more close to human reasoning. Much more closer to human reasoning. Because we human people, we don't think classically, right? If I ask someone about an information about a street or whatever, and they give me two different informations here, go here and you see a bakery, I go and see no bakery, or other people say other things. I don't derive from that Marco Polo is the Pope. Should I?
Like to be Pope.
He would like to be the Pope. No, he's Argentina, sorry. Okay, so, and I have two new rules because I have two new operators here. So these two new rules are this guy here above. So, consistent beta and inconsistent beta takes me everything, derives everything. Alpha, sorry, not beta. A consistent alpha and inconsistent alpha derives all possible beta. So, the notion of consistent and the notion of inconsistent are themselves subjected to classical reasoning. Okay. Another one, from zero, from no hypothesis, I derive either alpha, consistent alpha or not inconsistent alpha. I mean, the notion of consistent and inconsistent respect this law of excluded middle, the tertio non datur. Pardon here. Another one from that's principle of gentle explosion, in form of a rule. Consistent alpha, not alpha, leads to an explosion. And another one, if alpha is consistent, I can recover excluded middle for all possible sentences. So the consistent, in other words, the consistent operators, it restores classicality. It's a classicality operation.
Sorry, is consistent alpha a theorem?
Not here. Yes, good question. Good question. Could be.
Yes.
Could be, but not here. We can extend the logic to have that. That would mean that consistent itself is consistent in this kind of thing. Would be a very nice question. We can do it. There's other versions, but to simplify things, we're not taking that one.
I need a richer logic to have that as a theorem.
I
need a richer logic to have that.
Yeah, I need a richer logic. Yes. No, this logic here, just to make some things very clear, it's not any kind of many-valued logic. it seems to be that it would have like a four-valued semantics for you. We don't have it. Although it is an extension of this Belknap-Dunn logic of a first-degree entailment, which is four-valued. This logic here, when I added these new connectives, they are not many-valued anymore, right? So if I extend it properly, as Marcelo Cornelio and Abilio have done, we can reach a six-valued logic by extending it. But for the moment, we don't. So it's a not many-valued logic. It has a possible world semantics, like a cryptic semantics, and it has a simpler sound, complete and decidable 0-1 valuation semantics. I mean, the semantics made of zeros and ones. I mean, we can prove the completeness, then we can construct a model theory for it. We can extend it to first order logic. We can add quantifiers to it. We can even add model operators on top of it. We can do everything. So it's a basic little construction. I mean, very solid, where you can pile other things on top of it. Okay. Okay, next properties of this logic they are paraconsistent and paracomplete logic, not only paraconsistent. They are paracomplete in the sense that they can deal with gluts and gaps of information, like overlapping information and missing information. Okay, this is paracomplete scenario. So agents under this logic can believe in contradiction. At the same time, they are not obliged to believe in all classical tautologies because it's not plausible. This logic is able to express a distinction between a developing context where there's some positive evidence for alpha, but no evidence for not alpha. Suppose you are in a trial and you are collecting evidence for a crime, you are collecting positive evidence. On the other hand, the attorney, the lawyer on the other side is collecting evidence that the guy is not guilty. So the prosecutor wants to show that the guy is guilty. The defense wants to show that they're not guilty. They are collecting, as they do all the time, collecting information. So there is a developing context. There may be that just one side is collecting information, the other has nothing, right? This could be a developing context where one side has information, the other has nothing, or vice versa, or both are working on collecting information. From a conclusive context, where there's a conclusive evidence for one of the sides, like in a trial, right? They collect the evidences or proofs, or what they call theoretical proofs, but actually they are evidences. And up to a certain point, the judge says, okay, no more, let's go for a trial, and then let's conclude this thing here. So there is a sort of a dynamical movement from collecting evidence towards reaching a conclusion, reaching a conclusive, what they call conclusive context, where there is conclusive evidence for alpha, and so alpha has been established as true, and not the alpha is definitely rejected, or vice versa. Okay. So, and this connective, as I said, acts as a classicality operator when consistent alpha holds, excluding middle and explosion are valid again. That is, as I said, all the same, alpha, not alpha, consistent alpha is exploded, so it entails every possible beta, although it does not do without being consistent, and consistent alpha entails alpha or not alpha, although without this assumption, without this proviso, it does not attain the excluded middle for any possible alpha. Okay, so this is expressed by the new rules. We can have obtain some derived rules which say the following: from alpha and not alpha, we derive that alpha is inconsistent. I mean, from a contradiction, we derive an inconsistency, but not vice versa. So the notion of an inconsistent is bigger, is larger, broader than the notion of contradiction. And the other derived rule says, either alpha is true or not alpha is true. And if it's not the case, then there is a gap, then alpha is inconsistent. So these two rules mean that this little ball, this white ball is understood in two different contexts.
So you have a law of force excluded.
Yeah, in a certain sense. Yeah, in a certain sense. In a certain sense, yes. We also have a kind of topological semantics for the law that I would like to show you in another occasion, which shows you how hard it is to find the topological interpretation for this kind of symbols, which are sort of behaving in double sense, right? Okay. Okay, these rules are there, no problem. Now, just to make clear, modus ponens does not hold, so not.
Why modus ponens?
I show you. So you could think, okay, let's construct let's write this not alpha or beta and interpret this as alpha implies beta somehow. It does not hold unless I have alpha consistent. Okay, so I have to, in order to define a kind of implication that for which modus ponens holds and the deduction theorem holds, I need to add this consistent period. So if I add that again, I'm back to classical. Okay, some interesting properties here, blah, blah, blah. I don't think this is very much interesting. Let me go to the point before it takes too late. So non-standard probabilities connected to the logic. Okay, so many people think that probabilities are kind of a sister of logic or a brother of logic. So probability and logic are tied together. They cannot be separated. Probability and classical logic. Even some philosophers, as Adams, has said that logic, probability has to be connected to classical logic. But he was wrong. We can build new theories of probability based on several other logics, including this one. So what is the trick? How can I? Juliana explained that a little bit yesterday. I think you got it somehow, but I will explain again. So usually mathematicians, physicists, engineers, statisticians, they work with Kolmogorov theory, which is made on sets.
Sorry.
Sigma algebra.
Sorry, because this is, I block you because it's an important point, but before coming to that.
Yeah.
If you have no modus ponens, what is implication elimination? What do you eliminate?
We don't have an implication.
You have not cut.
No. We don't have implication.
I will not have implication.
We don't have implication. I mean, in order to have we only have implication for consistent sentences, statements. You know, our language has no implication. We can define that thing as implication under this proviso. Under the proviso of having it consistent.
Okay, so it's not only that you don't have implication as primitive, it's that you have no implication in general except for consistent sentences.
Yeah, exactly. Yes. Yes, that's true.
So you don't need implication elimination in general.
No, not even introduction, neither introduction nor elimination, right? Okay. Like
So you don't have any analogous of cut elimination because you have not cut. Or in some senses, the cut elimination is trivial.
it's trivial because if I restore, well, it will not be completely trivial because the logic is not so classical. But if I add this kind of implication, I mean, like define it, this is defined implication, right? Consistent alpha and not the alpha or beta. Then I have a kind of implication with nice properties. For this one, I can think about cut elimination. It's not going to be trivial because the logic has some small movement, but I can do it.
So you can prove a cut elimination for this,
Yeah.
this case.
Okay. Now, important point is this.
And in this case, you have modus ponens.
Yeah, yes, I do. Okay, so probabilities, I mean, as I was saying, for physicists, for engineers, for other people, usually it's measure theory. So like chomography did, you have a sigma algebra with operations, it's a kind of a generalized Boolean algebra in a sense. You construct it with sets. So sets or subsets of a universe, sets are taken as events. Events are subsets of things. Okay? Here we are working with another version of probability, what they call philosopher's probability, where we do not work with events themselves, but you work with statements about events. Statements, they are true or false. So for probability theory, for like the one Kolmogorov did, which is measure theory, it's the same branch of mathematics where they study integrals, measure theory in general, blah, blah, blah. They cannot say that something is true or false because they don't have logic. Here we are in a better position. We can mix something to be true and to have a higher probability or not. Okay, so we have two big tools at your disposal. And because we're dealing with statements, logic, we connect then this derivability relation to probability measures in the sensor here. So we just had some axioms which said
Something happened.
non-negativity. Sorry.
Oops.
Oh, there's. Why did I? See how can I? You know how to do that? Where? Some thing running here.
Connecting.
You go on share screen.
Oh, that's an internet problem.
There is no connect, there is no internet.
Apparently not. Apparently not. See, connecting problem.
Yeah, you're right. This looks like it's not correct.
Yeah.
But I am
That's
internet,
strange
I am
because-
connected.
Yeah.
Can you see whether you have some kind
No less.
Yes.
I am connected in Duron.
of
Where you are, in Chapman Open or in Duron?
I don't know. Chapman Open?
In Duron is working.
Or this Eduron
Oh, yeah.
sometimes is
That
not
looks
working
good.
very well.
I am connected in Duron,
Eduron. Is it okay?
apparently.
Yeah, try it. Put it. Is it switched off or?
It's off?
I don't know. It's-
What's this meaning here?
Yes, in Duron is working.
Oh. Are running out of battery? The battery. I don't know. I mean, sometimes the Eduron is not working well.
You see what is happened where you accept contradictions?
Marco had. Lisa had an idea.
I can read it to you in a sec.
What you did? An idea.
Yes, I
Yeah, an idea. Português aí. You know that word that starts with S, that happens sometimes. You know? This kind of thing that happens, this contradiction.
Do you ever think about finding another word instead of consistent, like classical? You could call it just
Classicality
Classical.
operator, classicalness, I don't know, let's invent one word. Like classicalness would be acceptable.
Mhm.
Well, you know, classical logic is stupid, but they have problem, they need classical logic to show.
Computers do not obey that.
So, but it is stupid, it causes problems, you know? Okay, now back to, thank you.
Yeah, in the natural world, there is no failure, right? It always goes on.
Okay, good.
Okay, then I was talking about this axiom here. So non-negativity means they are between 0 and 1. Tautologicity means if something is a tautology, it gets probability maximum, 1. Anti-tautologicity means that if something is a bottom particle, like this guy here, means alpha is entail whatever you want, so it's a bottom particle. It's a bottom particle, then its probability is 0. Comparison, if alpha entails beta, then probability of alpha is less or equal than of beta. And finite additivity, which is sort of makes the necessary connections between disjunction and conjunction, right? So P of alpha or beta is alpha plus beta minus this conjunction, like a combinatorial principle of inclusion and exclusion. Okay, so conditional probability is the same as in the standard case. If I define P of A given B, like P of, as Juliana explained yesterday, even gave a little proof of this Bayes theorem, P of A and B divided by P of B for a difference 0. This is problematic by itself because we have some cases where probability is 0 and things is not impossible. So having 0 probability and being impossible is not the same. But from this point of view, we have to accept that they are the same more or less. Anyway, there are other possibilities of developing a probability, making a different notion of conditional probability, like taking a binary operator. Popper did that. He developed an entire theory of probabilities starting from a binary operator which avoids the 0 probability problem. But okay, now here we are going to be as close as classical probability and statistics as possible. So we adopted this standard definition. So in terms of the evidence, P of A given B means how much the evidence available for B affects the evidence for A. This is very much complicated. The story of conditional probability is horribly complicated because some people want to say that if you have a P of A given B, P of A given B, this should be written as something like B implies A for somehow, but that's not true. You cannot do that because of the Lewis triviality problem. But if you change, like Paul Gray is working on this kind of thing, if you change this sign for other kind of implications or other kind of connections between B and A, you can do that. Anyway, it's complicated, but we're not going to do it.
Sorry, the case in which probability is equal to 0 is the case in which B and so probability of B equals 0 means B derive.
No. Just vice versa.
When the probability of B
No,
is
not
equal to
vice
0.
versa. Not vice versa.
Continuous case.
For instance, if B is a bottom particle, it has probability 0. But it has probability 0, it does not necessarily to be a bottom particle.
What is a case in which a probability is 0 that is not a bottom case?
Like it's something would be impossible with 0 probability, like the famous example of you trying to, you have a dart, you are launching your dart here. What's the probability of getting a rational number? It's
0 measure.
It's not impossible.
Yeah.
It's 0. It's 0 because it has measure 0, right? In comparison, it's a very thin space, like rational have a measure 0 compared to reals, but then it's not impossible to pick up a rational
Yes,
number.
but then you have a B that is inconsistent, but is not contradictory. Okay?
Yeah.
And so I can reason with B as an evidence. So in order to give a sense to the idea of probability of A against an inconsistent evidence, I need to deny that is inconsistent statement as probability 0. So a consistent statement have to have probability different from 0. Otherwise, I cannot define conditional probability on an inconsistent evidence.
Yeah,
I-
okay.
Okay?
Now you can think it this way. We were trying to be as close as possible to classical, to standard logic and standard probability with small difference as possible to make it clear what we're doing here. Otherwise, you don't.
But the same idea that I can reason for uncertainty include that I need to consider the case in which my evidence is inconsistent.
Yeah.
And I work on it.
Yeah.
So I need to be able to define probability of A
consistent-
on B
Right.
is being consistent.
But to be consistent, it does not mean to be the
But
probability
it
zero.
cannot be to be probability zero, otherwise I cannot give the definition.
No, it does not mean. You know.
Exactly.
Yeah,
That's
yeah. True. Yeah. So the non-standard schema, this non-standard schema for probabilities, as I'm showing here, can be adapted to many other logics. You can build a probability based on Lukashevich three-valued logic or five-valued logic or Gödel's logic or whatever. So if you follow this kind of a recipe here, you can have many different kinds of probability. Now, you may ask me, what am I going to do with so many probability theories? I don't know. As much as we can do with many different logics. It's not my obligation here to find application for everything, right? Okay. Some probability theorems which indicate that we have new tools at your disposal, like probability of alpha given beta plus not the alpha given beta minus probability of inconsistent alpha given beta gets 1. We have to subtract the inconsistent parts in order to recover what I had before.
The fourth excluded.
Probability of beta given that beta is consistent plus not beta given that the beta is consistent, this equals 1, as expected, because this is working like in classical logic again. Now, important one, probability of alpha and not alpha is not 0. It's somewhere between 0 and the probability of inconsistent alpha. It has a value. How much? I don't know. It's open to satisfiability problem. Probability of alpha or not alpha is not necessarily 1. It is between 1 and the probability of a consistent alpha. Again, it has a kind of limits, right? Now, number 5, if probability of a consistent alpha is 1, or equivalently, probability of inconsistency is 0, then classical probability works again. Probability of alpha or not alpha is 1, and alpha and not alpha is 0. So the degree of a probability of a consistent tells me how close or far I am from classical logic. Okay? So in a certain sense, probability of, as Alex was sort of suggesting, probability of consistent alpha defines a degree of a consistency of alpha or a degree of a classicality of alpha. How much is close to
But
classical?
this degree of consistency is an epistemic degree or is an ontological degree. So it means that you do not know exactly whether it's
It's
consistent
epistemic.
or not, or that it is not
Epistemic. Epistemic. Yeah, everything here is epistemic.
anything.
Our interpretation of paraconsistent logic is epistemic. We don't need any kind of dialectia as Graham Priest needs. Everything epistemic here. Now, the standard principle of conditionalization. This is, as Juliana explained yesterday, this is the basic of the epistemology of Bayesianism, or Bayesian epistemology, how we can make our updates. And in principle, we believe, Bayesianists believe that by making the updates, they are getting close to truth. Right? So, the probability assigned to the hypothesis before receiving new evidence is called prior probability. How do I compute prior probability in from the Bayesian point of view? I don't compute. I guess. I believe it. Bayesian probability is a tool to make you put into work your beliefs. Right? So I believe it, so I have a prior. Then afterwards, probability, when I get new evidence, that's why I need evidence here, it's called the posterior probability. There's a normal debate between frequentists and Bayesianists because some of them don't believe that this makes any sense. But the practice means that it is working very well, so I'm not going
So this
into detail here.
is very compatible with a subjectivist conception of
Yeah,
probability.
yeah. But for instance, Popper, Karl Popper and David Miller gave a proof that appeared in Nature, proving that inductive logic, this kind of reasoning that somehow is being made here in Bayesianism, has nothing to do with probability. They try to prove it. It's an enormous complication because many people wrote against it. You can find this discussion like they like 4 or 5 pages only in Nature. Some simple calculations try to show that there is no point in treating this kind of thing from point of view probability. But it's not true. I mean, we in practice, in engineering, everywhere, we think inductively based on probability. Even if they similarly proved it. Anyway, it's another question. So Bayes' theorem, as Juliana explained.
Popper proof depend on a very particular interpretation of probability.
Yeah.
That is the probability, what is it called? Oh my God.
Popper has this kind of, how do you call it?
Called probability
No.
as, I don't remember. Oh my God. Okay, in any case, it's required that if you accept
Kind of a crazy idea. This probability is
propensity.
propensity, exactly. Propensity. I mean, something is more propensious, how do you say? More propensity, propense, which word? Propense or what?
Propensity, this is what it's called.
No, propensity is okay, but the other, anyway, the adjective of propensity, what's this? I don't know. Nobody knows.
Proper.
No. It's not proper. To be propense, perhaps.
In Italiano is propenso.
Propenso. Sì, va bene. So, Italian is very useful. Bayes' theorem shows you that, as Juliana explained yesterday, if you, Bayes' theorem, so that if you get probability of H given E, you take probability of E given H, so the contrary one, multiplied by PH and divided by PE, and this is an obvious consequence of a real little arithmetic based on the definition of conditional probability. Okay. Now, in my opinion, this Bayes' theorem is a kind of miracle. It's the most simple mathematics ever, which is most interesting interpretation. Like you can travel, instead of going from cause to fx, you can travel back from fx to cause. It's like traveling back in time. That's why people in quantum theory are interested in kind of thing, in a certain sense. Okay. Now, this Bayesianism permits to make probability statements about data and hypotheses, not only on data. So this is a stochastic process that sort of reverses cause and effect. And then updating beliefs, you do, it's just exactly, this is the basic core of Bayesianism in order to compute the posterior probability. I mean, what's the posterior? After you get some evidence, you start from the prior one, but using this notion of conditional probability, which is A probability of H conjunction E divided by probability of E. You take your priors, taking into account any evidence, you get your posterior. Okay, that's a standard. Now, what we are going to do here, we are going to develop two new rules of conditionalization. This is not a theorem, this is a definition. They are sort of modus operandi, right? No, a new definition. The new definition is the following. In order to, in paraconsistent logic, now here in our logic, in order to conditionalize from B given A using negation, because let me remind you that we have two objects here, and I have contradiction that implies inconsistent, but not that inconsistent implies contradiction without some further axioms. So I have two operators at my disposal. The operator of negation and the operator of inconsistence, and they are not the same. So I have two possibilities of defining here the conditionalization based upon negation and based upon the inconsistent. So what do I do here? I just propose that it is B, probability of B and A. Before it was just divided by A, but now I sort of subtracted here the probability of this contradiction and B together minus the probability of contradiction and on A. I'm supposing that only A is contradictory, right? Only my new evidence is contradictory. I'm starting from something and I get a new, I could do the other way around, but this is make things simpler. I get some new evidence. My evidence can be problematic. My evidence can be contradictory, or in the second case, my evidence can be inconsistent. Always I have to be careful not to divide by zero, blah, 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 not by any negative numbers, otherwise I get out of a 0-1 limits, okay? Now, these rules of conditionalization, don't look at my slide, just look at what they say. They're saying the following. As much as I get probability of A bigger or consistent bigger or inconsistent close to zero, as much as inconsistent go close to zero and inconsistent go to zero, contradictions, the probability of contradictions also get close to zero. As much as I do that, these two rules get together and they get closer to the classical conditionalization rule. So the classical case, then, we are not inventing any new revolution in probability. We're just expanding the realm, the kingdom of probability, in a sense that everything, when inconsistent is small enough, close to zero, everything goes sort of collapsing. The two rules are collapsing and getting closer to the classical again. All are the same idea of classicizing or getting close to classical logic. Now we have two forms of a Bayes theorem. One of them based on negation, other one based on inconsistent. Obviously, I'm just making it simple calculations. That's a no novelty here. Now I'm going to give an example which I think is very much explains a lot. Okay, let's meet Pinocchio, and Pinocchio, as you know, she lies sometimes.
Why is
A lady?
woman a Pinocchio?
It's everywhere, so
It's political.
I'm not going to say Pinocchio. So Pinocchio is also a very nice character. Okay. So Pinocchio lies sometimes. The problem is, if she lies all the time, we are done. If she never lies, we are done as well. But she lies sometimes. How can you take profit of this complicated case where you're dealing with a liar? So you are rolling dice with Pinocchio. So suppose Pinocchio rolls a fair six-sided die without giving you any information. So she asks you about your...
But sorry, in United States, you all know which Pinocchio is a human, is common in the United States?
Disney exists. We write.
Yeah. It's true.
They invented Disney.
Okay, sorry.
This
They invented Disney, so here, I mean, everyone.
No, 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 you forget the Disneyland. I only remember Collodi, so of course.
So Pinocchio is rolling a fair six-sided die, and she asks you about your unconditional credence that the die came up 4. 1/6. You say, okay, my rational answer would be 1/6. This is a prior hypothesis. And then she tells you the following. Okay, I rolled the dice here, and it came up even. It came up even. Now, obviously, you only have it 2, 4, and 6. So you said, okay, it was 1/6 before. Now I change it to 1/3, obviously. Right? You change it to 1/3. That's your obviously rational update. But now, there's a problem. Sometimes she lies to you. We don't know if she's lying that time. If she tells you that, but this explains, okay, there I have a simple calculation here that shows you just to make sure that by using probability based on logic, you can do the same calculations that the statisticians do using their measure theory. Okay, but that's not important. That's not important. What's important here, there's a simple calculation. If you agree with me, you don't need any calculations to go from 1/6 to 1/3. Then it happens, however, that Pinocchio lies sometimes. And you know that she has lied to you 8% of the previous die, just for example, the previous die game. So you know it's very important for playing cards, right? If you know how much your opponent is lying, what's his statistic or her statistic of lying. You know that she lied to you 8% of the cases. So standard conditionalization is not robust enough to take profit of it. I mean, a classical player would say, okay, I don't play with you. Let's finish the game. But here, I show you that you can go on and take a profit of the lies in a certain sense. So in this example, I'm going to use this conditionalization. P of E is one which is half. Why? Because it's even or odd. So to be even or odd is very classical stance. When a die has only 6 sides, not even 7 or 5. So a die is okay. Only her information is taken to be incoherent or inconsistent. Right? P of H and E is 1/6. I mean, okay, because that's your prior probability of getting a number 4. The hypothesis H behaves classically because that's your prior probability. So probability of H and not H is 0 because it's classical. What is the only problem is it depends crucially on the probability of the contradictory evidence on what she told you. Okay, so you have a number here what they call X. It's the probability of P of E and not E. I mean, probability of something being the case, and she is telling you other way around. So this is 8%. 8% of the time she's lying to you. Now, if you apply here everything here, we just are going to compute probability of H given the new evidence E, but this evidence is contradictory. So what I have to do is I have to compute probability of H and E minus probability of H and E and not E, as defined before, divided by PE minus P of E and not E. So I know I have everything here, I have all the numbers. It remains to evaluate the probability of H and E and not E. So a reasonable evaluation is to see these kind of things as independent. And then I'm just, because for independent events, when I compute the probability of a conjunction, I just make the product. It only holds for independent events. So here, this probability is probability of H, which was 1/6, as you agreed to me, multiplied by X, which is the probability of E and not E. If you do this in our calculations, we obtain, I mean, just plug in values, we obtain a certain number here, 1 blah blah blah, 1 over 3 multiplied by 1 minus 3 minus x, okay, etc., etc. I have to be careful not to explode my limits of probability, being to be outside of 0 and 1, and then just by playing with these conditions, what do you call this? Conditions you contour, how do you call this? This outside conditions for
Constraints?
constraints, yeah, exactly. I have to put some constraints that x stays between 0 and 130, means she cannot lie. If she's lying, her lies is in this interval, then what I can do, I
Sorry,
can.
it is a value 1 over 3 is absolute in any situation.
No, over
So
3.
you cannot have a
absolute if
Pinocchio
she's
that
not
lies
lying.
50%
If
of
she's
time.
not lying to you.
Sorry?
If she's not lying to you, if she says, okay, it came up even, so it is, okay. Let me do it again.
How did you?
Your first
find
universe.
1 over 3?
Your first universe was like that. Your first universe had 6 events. 1, 2, 3, 4, 5, 6. In order to get 4, your bet is, that's the probability 1 over 6. As she says, is now it came up even. You say, okay, now you reduce it to 2, 4, 6. And you update your probability to 1 over 3.
Yes.
But she may be lying to you. Now, in my example case, she's lying only 8% of the case, would be 12 or whatever. She's lying on that. So because of that, you are computing, you are not going exactly to 1 over 3, but perhaps a bit less. How much less?
Okay.
How much less? So my calculations show you that you can exactly, you go from 0, 3, no, okay, you are doing here all the calculations, blah, 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 you go to 0, where is it? Okay, so how much I get here? Anyway, I have a bit less than 0, 3, you get 0.3. Before it was 0.33, blah, 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 which is 1/3. Now, because of this lie, because of this probability of lying, you go back, you go a little bit less, 0.3. More than that.
Okay.
0.3. So you're reducing, you're updating now. Now you can, this I did with alpha. You can reduce it, I mean, not continuously, but not linearly. You have a way to, now we are here, we are more or less in this region, okay? So as much as she lies to you, you reduce your posterior probability up to 0, okay? She lies all the time. If she lies 100% of the times, then you just say it's 0. Because it's completely lying, I go from 1/6 to 0, okay? So it's a very nice tool, in my opinion, because you can operationally deal with a kind of a measure to take profit of your opponent lies if you know something about him or about her. Okay? I don't know if you like it. I find it's wonderful for taking decisions. Like it can be, in principle, can be used to many other situations, including artificial intelligence or and other things, because you're sort of, you have more tools at your disposal now. You can reason with incompatibilities if you have a bit of information. If you know nothing, if Pinocchio is a random liar, she lies absolutely a random way, there's no way to do anything. Right?
You a suggestion. You should read for that a fantastic book that apparently has nothing to do with it, but in fact by Buchwald and Feingold. That is called The Newton and the Origin of Civilization. It is a book on Newton about the history of civilization. And there are discussions of some manuscripts by Newton that are not very well known, but he developed a lot of this argument, in which Newton say exactly that. Say the first one. Newton say, it's not true that on the base of a non-certain information, I cannot evaluate, I cannot try information. Science can be done also on the base of uncertain information. And he developed this position against other scientists in the point, said, okay, if it's uncertain, I can do nothing. Say, no, I have to evaluate a document from about the history of civilization. I do not know whether they are trustable or not trustable,
Nice.
but even if they're not trustable, I elaborate a process in which I can try some information that of course is not certain, but is still positive.
It's better than nothing.
Exactly. That is a very nice point.
Okay.
And
Okay, wonderful. I like it.
Feingold and Buchwald, Newton and the Origin of Civilization.
Who is the other?
Feingold and Buchwald
Ah,
are two historians of science.
okay.
And the book is called The Newton and the Origins of
Juliana's
Civilization.
taking notes on that. Okay, very wonderful. Wonderful to hear that. But not only Newton, but also Cantor developed a certain tools in set theory in his Mengele theory of sets by taking profit of some incoherent sets that were sort of classes, more or less, right? Anyway, this is another thing. So this is one application that I think is very much interesting. I mean, I like it, and I tell you the following. Yes, you have a question?
Yeah, I wanted to, there's this whole tradition about making experiments in psychology that kind of prove that people don't reason rationally. And those involving probability are very well known.
Yeah.
So now you have a different account of reasoning with probability. So I'd be curious now whether that would lead to some new interpretations of these experiments, or also to the design of experiments.
Yeah.
So here at Chapman, for example, we can run
I'll
experiments.
be very much interested in doing that.
And so we could design an experiment, go into the lab and see how people make decisions. And maybe we make decisions that can be better explained with your
Wonderful.
probability.
Music for my ears. Okay, wonderful. I'm very glad. You know, this guy, you mentioned a book some days ago, some weeks ago, Van Lambergen.
Yeah.
Van Lambergen is a guy who's doing currency.
Yeah, exactly.
And I know him, he would be very much interested, if he agree. But okay, now I would be very open to any kind of project you have in mind.
That's another question.
Oh, sorry.
I think I wasn't understanding why Pinocchio lying involves a contradiction.
Okay, this is a philosophical point. It's a very good philosophical point. Why is she lying causing a contradiction? Because there's a contradiction between her statement and the world. Right? Contradicts the world. Now you can tell me, you can say the following. Well, it's not a contradiction, it's just an inconsistency. But you decide what's an inconsistency or a contradiction. They're not the same, they can be the same, but actually, philosophically, a lie is a contradiction with facts in the world. That's right.
Yeah, so it says the opposite of what the fact is. That I see. But it doesn't seem like a contradiction in the sense of,
Well, it's not that there is the world has contradictory objects like dialetia or anything like that, or metaphysics. It's just your statements. Just a incoherence or a lack of alignment between your epistemological attitudes and the world. Right?
I was thinking that, that kind of relation is more like an incompatibility relation rather than contradictory.
Incompatibility is a kind of black ball. So anything you can do. I chose to use, I could have used the black ball approach. I tried to use this contradiction approach. I mean, trying to see her statements as a contradictory statement rather than as inconsistent to make it simpler, but it could do. Would be the same result, okay? Now, this is one example. I don't know how much time I have, Marco. Go. Okay, go.
Go up to slide 41.
Yes, I have another example.
You are only,
Yeah, I think you're
you
going to
can
be.
go only to 41 and not more.
Yeah, no. I have another example that I think that would be interesting for you guys in this program of MPP, because it concerns philosophy of science. Exactly. So it concerns the confirmation theory. So standard Bayesian confirmation theory, for this standard Bayesian confirmation theory, an evidence E is said to confirm a hypothesis H for an agent if and only if the agent's credence on H would be raised by conditionalizing on E. Or in direct terms, an evidence E confirms classically. Sure, you have a hypothesis and you have a new evidence. This evidence confirms classically a hypothesis H if and only if by conditionalizing you get something bigger. I mean, you get something bigger. So you had P of H by conditionalizing on the evidence, you get something bigger. You rises your degree of confidence, your degree of belief in your hypothesis. That's why it's confirming. Right? Is this clear? I mean, this is a very simple idea. New evidence confirms if I am updating with the new evidence and get something bigger. Otherwise, it's not confirming. Okay. But it hides a difficulty because it works on the non-deductive part of scientific theories, and then it works on, I don't like to say that, but inductive part or non-deductive. Logicians don't like to say that induction is logic somehow. It's just the complement of one. That's another point. Now, let me give you an example here, a real example, the enigma of Mercury's perihelion. Perihelion is likely to be closer to the sun, like peri in Greek, and helion, sun, blah, blah, blah. Perihelion is to be close to the sun. So this problem, namely the problem of all the evidence, says the following. An event E is unexplained by the available scientific theories. Okay, there's an event that's explained until a theory H is discovered and accounts for it. It's explained, a new theory appears and accounts for it. Okay. The observable E, previous to the theory, look like, pay attention because this phenomenon was before the theory. Okay? Before the theory is called the old evidence. It should confirm H since it explains it. Because H explains the old phenomenon, H should be said to confirm because it explains. I mean, confirming according to this numerical definition. So the Mercury perihelion anomaly, it was the following. The dynamics of Mercury could not be explained by Newtonian mechanics. It was sort of crazy. Mercury was sort of crazy closer to the sun. Nobody could understand what's going on. So Newtonian mechanics was able to explain almost everything, including comets coming from every 1,000 years, but not Mercury. Why? Then came Einstein's theory of general relativity in 1915, offering a new explanation. In general relativity, gravity is not a force, but this is a bending of space and time. So because of the sun was so massive compared to Mercury, was causing some problems or some differences in bending of space and time. So like a massive object like the sun, curved space-time around them, changes Mercury orbit slightly. It's a wonderful explanation. Wonderful explanation. Genial. Right? Okay, just have some nice things to say. You know what's happening to Mercury's perihelion? I know, it's just so anomalous. Wow, Mercury is going crazy. Now, it explains very well, but according to the numbers of statistics, it does not. No? Mercury anomaly formally does not confirm the generality or relativity, which explains it. So something's wrong. How is this possible? Indeed, when E is all the evidence, the prior degree of belief is maximal because it's a phenomenon. The prior degree of it's there.
Yes.
Prior, it's one. But because it is one, it is not confirmed. Why? Because if you make these calculations, if you do this calculation here, P of H taking E into account. I mean, the new theory take the evidence into account. You do the following: P of H and E divided by P of E. This is P of H and E is the product of them. In any case, is less than P of H, not higher, but bigger. That's the problem. So why is this caused? Because there is no way to reason with that kind of thing. It is there. So in our theory, we can think about one thing. So let's apply our evidence, our confirmation here, new kind of confirmation, because okay, I do all the calculations, blah blah blah, and then what I have here is an evidence confirmed as an hypothesis, if and only if this inconsistent kind of update is bigger than H, if and only if P of H and E minus the incoherent part divided by P minus blah 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 is bigger. Okay, for this kind of thing cannot be zero. So if I apply this thing here, I have a way out of this dilemma.
But, sorry, that I do not understand. If E is a fact, how can it be inconsistent?
Excuse me?
E is a fact.
It's a fact.
So its probability is 1. And then now you say
It is one, but it has a
of
certain degree of
inconsistent.
incoherence.
So we have inconsistent fact.
Inconsistent facts, you have inconsistent knowledge about the facts. An inconsistent epistemological
So I
account.
that I'm not so sure that mercurium has a anomaly.
You are sure, but you are not measuring well. Your theories were not predicting well. They are not perfect. Your measure are not perfect. Your epistemological attitude towards it is not perfect. That's some incoherence. That's one possibility to get out of this way, go out of this maze.
I am so sure that Newton is right, that there is an event that contradicts Newton. I think that the error is in the event, is not in Newton. That's what you say?
It's not there as in the Newton. I mean, Newton is not explaining it. It's relativity theory that's explaining it.
No, I understand. When you say that E can be inconsistent, even if it is a fact, what you mean is that is a fact that I can doubt about. There are facts that I do not doubt and facts that I doubt.
I doubt about it because my theories are not perfect.
So any fact I can doubt about, or only someone?
Any fact that's causing troubles to you. I'm not doubting about that this is right. I could be.
We can all of us platonic.
It depends on, it depends on your account, on your possibility. It's not a metaphysical necessity here. Just a possibility.
Okay.
Rational tools at your disposal. So in any case, if you take that into account, the calculations are here. If this guy here, this part of this denominator is almost zero, mean probability of E is close or more or less close to the probability of being inconsistent. If inconsistency is big enough for a certain measure, I don't know how much, then this is not less than pH, but can be bigger. So what happens is it's not necessarily less than, and the problem for all the evidence may disappear, right? So in a certain sense, that's one possibility out. That's one possible way out. I don't say that this is a real solution, but this is a way of computing with doubt. A way of computing with doubt. Is this the best solution? I don't know. But this problem for all evidence is a problem that they don't know what to do. Something's wrong. So, or the Bayesianism is wrong, or the measure is wrong, or the definition is wrong, or the idea of that something explaining and not confirming is wrong, but or is correct. I mean, confirming does not mean explaining does not lead to confirming. I don't know. There's some complications here. That this is a possible way out of the dilemma. Anyway, are these probabilities really promising? I think they are. They seem appropriate to model evidence and degrees of evidence, paracomplete and contradictory, because it happens all the time. You're going to have missing information and overlapping information. It happens all the time. Huh? The probabilistic semantics is flexible enough so that P plus PDA plus P not A can be greater or less than 1, interpret respectively as conflicting evidence and on little or no evidence. It also addresses this problem, namely the problem of perfect fit, which is recognized, for instance, in this Stanford Encyclopedia of Philosophy, in this entry, namely Bayesian epistemology. It said the following: probabilism demands that one's credence fit together nicely. For example, some credence are required to sum to exactly 1, no more, no less, a perfect fit, and to require that everyone belief can comprise a perfect fit is not a good thing. Usually it's not the case. I mean, beliefs do not behave this way. So we have a certain way out of this problem as well. This operator interprets as behaving classically or classicizing the subject of degree when probability of consistent alpha is 1, the classical behavior on PDA is restored, and so evidence available for A recovers the loss of a standard probability. It encodes classical logic, it's flexible enough in a certain sense. I am talking about expanding Bayesian epistemology and not destructing it. And expanding logic and not being in rebellion against logic. I think it's a good thing. Again, our battery is just finishing. This chapter is part of our book that by Marcelo Cornelio and Abilio Rodriguez and myself. Is going to appear on Synthesis Library, namely Contradiction, Evidence, and Truth, Epistemic Interpretation of Paraconsistent. I am also glad to tell you that this paper won a prize 2022 for the Brazilian Logic Society for the better paper in 2 years. Okay, thank you.
Thank you very much, because now that we know that we can work on uncertainty, we can also learn something from your talk.
Yes, thank you.
So in some sense, your talk confirms itself.
Yes, I'm glad to hear that. I'm very glad to.
Okay, questions?
Yes, please.
Just so that I understand the perihelion example, so the degree of the non-classicality of the event, are you arguing that that's coming from the difficulties inherent in like empirically verifying it, or is it because it's causing issues with an existing theory, like Bayesianism? Or what exactly, why the non-classicality exactly? I wasn't quite sure on that.
Let me see if I can understand what it was. Well, it's a matter of deciding. If you decide that there's some problem because they are deviating from logic in a certain sense, they're deviating from the canonical laws of standard logic, and we say that's being incoherent, inconsistent, deviating somehow, and then how can I measure the degree? It's not a matter of logic. I mean, you have to make some experiments, right? It should be something experimental. Like in the statistics, it's all the same. How can I know that a dependency between two events by using mathematics? I cannot do. I have to go to run some experiments. That's what people do, right? So I think I suppose this answer to your question.
Well, yeah, in this particular case, though, where the fact in question, the E, is presumably the deviation of the perihelion, are you saying that that particular event is non-classical because just of difficulties in empirically verifying the event, or because it doesn't agree with the Bayesian confirmation theory?
Well, my point would be the following. If you decided to regard it from this point of view, and it helps you to solve, is a kind of a nice way of getting out dilemmatic problem, right?
Yeah.
But that's just, it's your decision.
Okay. So you have no stance
Yeah.
exactly on where that's.
No,
Okay.
mathematics and logic, I cannot solve it.
Sure.
Yeah, I see there was another question. Sure.
Yeah, I was going to ask if you have thoughts about the preface paradox, or
Which one?
the preface paradox, because it's one kind of classic problem for coherentists, in epistemology. So the thought is like you could take all the propositions that you believe, and your view's adjunctive, right? So you conjoin them all, and so if you conjoin them all, then you can believe that everything that you believe is true. But most people think at least one belief that they have is false.
Yeah.
So you
Yeah.
generate a
It's
contradiction.
the paradox of the preface.
Perfect. Yeah. No, that's a very nice possibility. I mean, we have not worked on this direction, but this is very new. That's completely very new. But yeah, you're right.
It struck me you might have.
Yes, you are. I think you are completely right. So the preface paradox, the St. Petersburg paradox. St. Petersburg.
Oh, okay.
St. Petersburg paradox or something like. I mean, it's more like that. So if you buy a lottery ticket, your probability is almost zero. But you can win. And it's more or less like the preface, right? So if you add everything, 0, 0, 0, 0, 0, but does not get to 0, because it gets to 1, someone wins, usually, right? And also this Linda problem, that was Linda problem, the Kahneman and Tversky with this Linda problem. But Linda problem is like that. You say, okay, Linda is a young lady. She went to college. She was an activist, a feminist. Is she working for a bank, or is she working for a ONG? No, it's ONG.
Yeah.
I mean, usually people say, "Oh, she's working for the ONG." Why? But she was in the college and studied economics and was the best one, so he probably worked for the bank. So he will make you wrong decisions about little things that could be, as Alex suggests, explained by this kind of reason. I don't know, but we have not. It's a good idea, but we have not gone into this direction yet.
Yeah, well, partly the reason I was asking is, a lot of people think it's the adjunctive is to blame there, that we shouldn't let you do conjunction introduction.
Yes.
But you are adjunctive.
I'm adjunctive, but it could not be. I could just change my. I mean, I have two boxes at my disposal, right? I can be adjunctive, I can be not adjunctive, I can use another logic. If it is open an avenue. Then you can change logic, change the positions, and change your epistemological positions, and do other things. I don't know exactly where does it go.
So how do you resolve this lottery problem that,
I don't know. I don't know yet. I mean, I'm suspecting we can apply this. It's not easy. It's not easy. There are many problems like that. I mean, problems that they are, it's not people don't reason well. People sometimes reason in a way that's not predicted by the theory.
is there a classical explanation of that problem?
No one that I know.
'Cause I never read
One that I
about
know.
that one. You know,
No one that I know.
Never heard about.
No one that I know. It's like the following problem. A soldier goes to the battle and says, okay, I'm not going to die for that. I go home, I'll escape. And then voting is my vote makes no difference. If everyone thinks that their vote makes no difference, what happens to the democracy? Right? The same story. Then you have to convince people to go voting, giving some money.
I have a question.
Yes.
The Pinocchio case.
You like it, right?
Yes, I like the Pinocchio case because it's a very normal case. We are also always dealing with Pinocchio. Any one of us is a Pinocchio in that sense. But the point is that I'm wondering whether your representation of the situation is not a little bit artificial. Because what your system, if I understand well, I can derive value of probability with parameterized with a value x that you have to take to have a certain.
It's probability of E and not E.
So in this case, you say that is 0.08. Okay. But the case that we have in Pinocchio, the Pinocchio case that we live with in a day, is cases in which I know that someone sometimes lies, but I do not know how much he lies. So I have no possible estimation of this number X.
If you know
it's
nothing, there's nothing.
Not simply that this number can change from case to case. The problem is this number is simply unpredictable because what I know of you is that you sometimes lie. But I don't know that you lie 0.08 or 0.09. And so, in terms you have positive values under a number that you have no way to calculate. So, what sort of information is? This is my question.
What I'm saying, if you know, you can take some profit. If you know nothing, you get nothing.
Yes, but yes. So, but I say to say, your Pinocchio is a very strange character because it's not someone that sometimes lies. It's what happened to any one of us. It is someone that lies in a constant probability. That is sometimes that never lie. How much time do you lie in your life? What is the probability of lying?
Each time.
Exactly.
Insurance companies know that people lie sometimes to them.
Sorry?
Insurance companies know that people sometimes lie to them.
That is a good
They
way.
pay someone to steal their cars, or they set fire on the car, or they say,
So
there are some cases, and they reason with that.
I can calculate X on the base of a frequentist
Yes.
statistical.
Yeah,
So
sure.
I can make
That's
a
the only
statistic.
way.
Yes,
That's the
I
only way you
make
can
a
know.
statistic in which I know more or less what is X, and then I put, okay, that's a good argument.
Yeah, that's it. I mean, that's coming from real life.
Okay. For example, when I tell to my students, you have to come to class, and if you don't come to class, you have to justify. They write a message, and they have any incredible reason to not to come, and I know that they always lie. But even if they know that I always lie, my job as a professor is to behave as if they did not lie.
Say, okay, Claire, take care of you. It's not a problem. So, but statistically, perhaps sometimes they're right.
Well, they are clever. They are more clever than the professor. Well, good for them. Good for them.
Okay, other question.
Why? No.
I don't know.
Think, what is it?
No, nothing.
Okay, good.
So we have a philosophy of mathematics, philosophy of logic, and philosophy of science in this talk. So I have another question. Your paraconsistent logic is a quite peculiar case of paraconsistent logic, exactly because differently than other paraconsistent logic is a generalization of classical logic instead of being a negation of classical logic. And this is an aspect that I like very much. But my question is, you can arrive to similar result also with ordinary paraconsistent logic, or the fact that your paraconsistent logic is not ordinary in this sense, is not only a philosophical nice aspect, but has also practical aspects. So it's because of that you can construct that, or it's independent.
It's because, this LFIs, the logic of a formal inconsistent that we sort of invented or discovered or worked there. It's so because of this idea of separating contradictions from inconsistency, and also non-contradiction from consistency, blah, 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 make that separation, makes us able to reconstruct that many of your other paraconsistent logic is existing, like the ones that people in Israel work, in Belgium, blah, 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 many old ones, this Jaskowski logic, even Jaskowski.
So you want to say that not only classical logic is a particular case of your logic, but also the other paraconsistent logic is a particular case of
yes.
For example, you can have a logic in which any statement is inconsistent.
Yeah. Or different
and
kinds.
This is, I suppose, Priest paraconsistent logic.
Priest, no. The Priest's logic here, we cannot recover it because it's so weak. It's very weak that it has no room for defining this inconsistent operator. But if you other logics, we can. So Da Costa's logic, all of them, Stanislav Jaskowski logic, Batten's logic, dynamic logic, people in Israel, I don't know, Avron's logic, other people, and many other, like and also this, several, not all of them.
And you can also take as a particular case of your logic other sort of not classical logic, for example, not, I don't know, intuitionist logic, or not, what is called?
Many valued or...
The one that, oh my God, non-conservative. What is called the logic that when a theorem is proved that it can... Oh my God.
Relatedness, dependence logic.
Relevance logic.
Not relevant, also relevant. But my example is a logic in which you prove a theorem, but this theorem can stop to be a theorem. It's not...
I don't know that logic.
It's not conservative. It's not. I don't remember the name of it.
Oh, I see. By Boëthius, Aristotle, this kind of guy.
Okay. No.
Yes. No, some of them I can.
Connective logic.
Connective logic. I think it's connective.
In any case, you can reconstruct other sort of logic.
Some of them I can, some of not I cannot. We can do many, like infinitely many, including 3-valued, 4-valued, some of them. If they have paraconsistent character, we can do. If they're not, for instance, not Lukashevich infinity logic, it cannot be recorded in this kind of system. But we can, for instance, add modalities on it. Like everything you said, like We don't talk about
So
modality.
you can reconstruct model logic here?
No, it's not like, you can put modal logic on top of it. You can talk about paraconsistent modal logics. Right? And you can also find some possible world semantics for this kind of logic, exactly for this one I talked here today. So you're sort of approaching many branches of logic, put them together somehow, not all of them, but some.
I'm looking for the name. And
Connected, I think it's connected.
okay. And your semantic, you have different semantic, or how do you work the semantic?
The semantic here, there are two kinds of semantics. One of them is this 0-1 semantics, this valuation semantics. Valuation semantics, and we also have a possible word semantics.
So you have two semantic, and you were speaking of a topological semantic.
Topological semantics we are developing. I have one I can show you if you like, but I could not prove a completeness for this topological semantics yet, like they do for intuitionistic logic, right? So intuitionistic logic, they have a very nice topological semantics where they can prove completeness. In my topology here, I could not, for the moment, prove completeness, but I can show you the ideas.
But in that case, you just do representation, right? So here. also
Yeah.
probably you-
Yes, yeah, but I would like very much to do what Dana Scott did for this intuitionistic logic. Right? This
No
kind of-
monotonic logic is what.
no monotonic, well, I don't know. Perhaps some connections, but no, not all of them. Not all of them. No monotonic, no. No, my hours are monotonic. You know, Dana Scott proved that by this, if you interpret intuitionistic logic, the open sets as values, then you can do very well and prove that any theorem can be represented by an open space on an open set. I could not do that in my topology yet. I have an interpretation, topological interpretation, but not a topological completeness. For the
So what
moment.
are your algebras? What kind of structures are they?
I don't know. So some very weird kind of topology with the algebras, I don't know. I know that the algebra of Klopen sets, I can show you this, the idea is very nice. So, because you know, I have this black ball working in a very strange way. Sometimes I work with open sets, sometimes with closed sets all together, closed and opens together, and sometimes just Klopens. So classical logic will be restored by Klopens. Okay, Klopens have a Boolean algebra. That's why. But it's still a work in preparation. Still work in preparation. Maybe you guys can help me.
Okay, other questions? So thank you, Val.
I thank you.